Swayam Prabha. Digital India. Educated India.
In the last few classes we had seen the different cooling techniques, namely the film cooling, radiative cooling and regenerative cooling. These are primarily used in liquid rocket engines where you have liquid, or if you look at radiation cooling, it is primarily for satellite applications. Now let us look at how we cool a solid rocket motor. Okay, if you look at a solid rocket motor, as I said earlier, the heat that is coming in to the nozzle is something that needs to be taken care of. Other than that, if it is a port burning configuration, the propellant itself acts as a thick insulation layer. So you don't need to worry about cooling the thrust chamber or the entire motor, but only the nozzle portion. Now in the nozzle portion, this is a more acute problem than in liquids, because you essentially do not have any liquid on board, okay, and yet you need to have cooling. Okay, and let us look at what are all the techniques that are available and how do they cool the solid rocket motor. Now I remember writing this in with regards to radiative cooling also. There are a few books that say radiative cooling, heat sink and radiative cooling, okay, because it just acts as a sink and then radiates on the other side, okay. But there is also this method that has been used to look at the throat region of a solid rocket motor. Now if you remember earlier lectures, we had said that throat is a very critical region because the highest heat flux is at the throat. So you need to cool it, otherwise it is going to damage the throat region. Now one way of cooling it is to use high density graphite as shown in this figure. This is the throat region, right, and you have high density graphite here which acts as a heat sink. Now heat sink is something like this. If you have a particular thickness of this material, and if it is a high temperature resistant material, right, then if you look at how the temperature profile is for this material, it is something like this shown in A here, that is into the solid the temperature decreases, and depending on the thickness this temperature is achieved, right. So you need to know what is the thermal profile thickness, in other words, right. And if you look at this figure here, you see that there is high density graphite and there is a backup material. There is some phenolic, asbestos phenolic, and also a metal backup. As such, the graphite can take high temperatures but not high pressures. Okay, you cannot use it to make the motor casing itself, right. So you need a metal there, and this could withstand high temperatures and could be used above the metal portion. So what we need to know is how thick should we have this graphite. To do that, if you remember, this is a problem of unsteady heat conduction, okay, and you can solve this, and the thickness is given as, thickness of the thermal profile is given as where alpha is nothing but thermal diffusivity, that is in meters square per second, and T is operational time, right. So depending on these two, you will get a thickness, right. It also depends on, if you look at this figure here, it also depends on what is the allowable T naught you can have on the other side, right. On the other side, I remember I said there is either going to be a metal or a asbestos phenolic. So what is that temperature that you are looking to have on the other side is what determines what is this thickness going to be, okay. So depending on that, you can choose the thickness of this throat region with high density graphite. The next technique that has been used is ablative cooling. Okay. Now, ablative material as such is a material that consists of two different things. One is it has a base material and a resin. Okay. Now, if you remember our discussions about solid propellant and how heat is transmitted in the solid, right. We had this equation for the heat flux at the surface. That is right. Now, if you are looking at this ablative cooling, what happens here is there is this resin portion that vaporizes. So, it absorbs heat to change its state from solid to a gas phase. Okay. As this heat is absorbed, it cools the rest of the material, and there are two kinds of heat resistant ablative cooling techniques that are available. One is charring and non eroding, as shown here in B, and the other one is charring and eroding or ablating. Okay. The basic difference here is, in this case, charring and non eroding, it forms a char, but the char as you see here, even in a flow, cross flow, this does not get eroded, it stays as is. Okay. So, if you look at how the heat is going to be transferred, there is a new material that in a sense you are going to have, which is going to resist the heat transfer, right. You have now when you started out, you would have had only two materials, one is the virgin material and the other one is the charring material. As time progresses, you are going to have three layers, with the char layer increasing and the virgin decreasing. Okay. Which means that you can see here very well that the temperature profile through these decreases, and on the other side you can have a very low temperature. So the essential idea here is to have a high QS as possible, right? Then if you have a higher QS, no matter what your TS is going to be, if you have a high QS, then this T naught is going to be lower, and more so if you have different layers of these material, right? And the next set of materials that is used is charring and eroding or ablating material. In this case, because of cross flow, the material gets eroded, and you are going to have a region which which is if this were the nozzle earlier indicated by the dotted line, then that portion is going to move to this new line, right? So the area is changing, right? So area is increasing, and therefore the gas phase, if you see, is coming here as the charring portion moves into the virgin material. It still has 3 layers as in the other case, but the thickness of the char layer is very small here, okay, and the charring layer is the same thickness, and the virgin material after that. So with this you can have a lower temperature T naught at the other end, right? Well, this is in some sense the same idea which people use to burn camphor on their hand, right? You've seen that people can hold camphor on their hand and have it burning and do the arati, right? Essentially what they do is camphor burns, so the temperature profile in the camphor will be something like this, right? So you will have a fast burning here, and because of which on the other side the temperatures are really lower until the flame comes and hits the other portion. But what they usually do is they will have a layer of oil, right? So that protects their hand at the time when the flame reaches the other end, and if that is a very short time, it will go off without any major damage to the hand. So in a way, one good way to protect the material is to have something burn off, right? In that sense it is taking away all the heat, and that is what happens even inside a rocket motor as well as in ablative cooling. The materials used for this are silica phenolic, and carbon phenolic. This is the resin part, which upon heating absorbs the heat and evaporates. Okay. So a combination of if you look back at this picture here, if you look at this picture here, this is the convergent portion, this is the throat, and this is the divergent portion. This is the axis, so we have shown only one side of the axis. Now if you see here, the highest heat transfer is near the throat, which is protected by 2 layers. One is high density graphite and then a layer of phenolic resin, and after which the heat transfer coefficient reduces as you move towards the exit. So therefore you can use some kind of ablative material to cool it, right? So using a combination of both ablative material and heat sink, a solid rocket motor throat is or the nozzle is cooled. This is the same cooling technique that can be used in a hybrid rocket also, primarily because hybrid rocket, as we will discuss a little later, will have a fuel and it is also a port burning configuration. So, the fuel itself protects it in the combustion chamber, and only the nozzle needs to be cooled, which can be cooled using this kind of technique. Okay. So, we have discussed the various cooling techniques that can be used to cool both the nozzles and the thrust chamber. Now, let us look at what are the penalties and where do we use what kind of cooling. If you look at the different kinds of cooling, one was heat sink, then ablative and film cooling, radiative, and lastly we had regenerative. Okay. Now, various considerations that we need to keep in mind is, one is operation time, then the limit on PC. Remember when we discussed the equations and how we can rewrite the heat transfer equation in terms of pressure, right, using m dot is equal to PCAT by C star, we found that if you go to higher pressures, then the heat transfer coefficient will be higher. So, in a sense there is a limit on the chamber pressure, and restart, throttling, pulsing, and what are the penalties with these kind of cooling. Firstly, regarding the operation time, if you look at the heat sink, if you are given a particular thickness of the material that you can use, there is a upper limit on the time that which you can allow it for operation. Okay, because if you look at a steady state, then the steady state would be at, if it is a large time, then the actual chamber temperature will reach the other side also, if you are giving it a very large time, and if you are not taking out heat on the other side. So, so in a sense the operation time is limited if we use a heat sink, and same is the case for ablative cooling. Here it is less than 20 minutes, and then you have film cooling. Film cooling, if you look at it, you are constantly pushing out some liquid on the periphery. Therefore, there is no limit. As long as you have the liquid on board, you can keep doing this, and there is no limit to the time operational time. And this should be the same for regenerative cooling also. What about radiative cooling? Do you think it's going to have some kind of limit? It should have a limit because it is also in some sense a heat sink, and then on the other side you have radiation taking away the heat. So this is something like typically 1 hour. Okay. Now limit on PC, heat sink obviously cannot be unlimited, so this is again limited. This is also limited. This would have no limit as long as you have the coolant on board. This is also no limit. This is restricted to something like less than 10 atmospheres. So if you look at radiative cooling, it's only applicable wherein the operational time is also not very large, but the thrust of the motor is also very small. Now there are a few things that are possible only with a liquid rocket engine, that is restart, throttling and pulsing. Throttling is you can change the thrust level, okay, by adjusting the flow rate of the liquid. Pulsing is as we had discussed earlier with reference to monopropellant thrusters. If you look at the thrust versus time curve, it will have something like this. So there are short pulses of thrust, and there are no also times where there is no thrust. So what about heat sink? Can we have this with restart? Right? It should be fine. The only thing that will have a problem is regenerative cooling, because if you look at regenerative cooling, when the motor switches on, the flow in the coolant pipes might not be that good, because there is always some propellant that will be trapped, right, and that would have absorbed some heat and would have been a gas or something like that. So you need to be careful in only the regenerative cooling. So you cannot have too many restarts if you have regenerative cooling. Till the time it reaches some kind of steady state, the flow will not be established, and that might cause harm to the motor casing itself. So you need to be careful while using regenerative cooling, but otherwise the rest of the things it is fine to have as many restarts. Then what about throttling? Throttling other than these two, right, you are increasing the thrust level or decreasing the thrust level. Again there are issues of what is the flow rate through the coolant pipes, or how quickly can you take off heat or through the coolant pipes is an issue, right. If you are going up in thrust, the coolant pipes could be having a lower flow rate, and therefore it could be detrimental. So in these two cases it is limited, but otherwise for the rest of them throttling is no problem. And pulsing, in this case it is simply not possible. Okay, and this is in some sense again limited, because you have to have a flow on the surface of the chamber itself. But for all others this is fine, except of course ablative cooling, because ablative cooling, if you look at it, if you are wanting to have a very sharp cutoff, and if you are having an ablative material that chars and erodes, right, there is some amount of gases that are going to be released. So the thrust cutoff will not be as sharp, and you could have a residual thrust. Okay. So in this case, so let's now look at what are the penalties involved in using each of these techniques. These two, it's only the weight that is a penalty, because depending on the time of operation you need to have a certain thickness, and depending on the density of the material that you are using, it adds to the weight of the system. So in both these cases weight is a penalty, and in film cooling, if you remember, we are using one of the fluids, that is fuel on board, and this is not contributing a great deal towards ISP, right. So in a sense the penalty is here ISP, right. It is not contributing towards producing thrust in that sense. If you look at it, you are going to operate it at a particular O by F. It is not that it does not participate in the combustion or something like that, but in the chamber, right, if you are wanting it to be used as a coolant, you do not want it to be participating in combustion, right. Ultimately it will happen, but if you remember, what you want to do is the length that is available is only up to the throat. If it burns further beyond that, it is not going to contribute towards thrust. If the pressures and temperatures are increased beyond that, that is not going to contribute greatly towards thrust, because we know from thermodynamics, if you add heat at the highest pressure, that is the one that is going to give you effectively a better efficiency, right. If you are going to add things, if things are going to burn later on beyond the throat portion, they are not going to contribute greatly towards thrust. Although I am not saying this will not burn, right, this does burn, but it is only a matter of where it burns. It could as well burn in the atmosphere beyond the nozzle also. So in that sense, the ISP, the delivered ISP, what I am talking about is how much of propellants you are carrying and what is the overall specific impulse that you get, that will be lower. Then with regards to regenerative cooling, if you remember, when we talked about regenerative cooling, I said this is mainly for high thrust and long burn duration engines, and I spoke of the space shuttle main engine, which is a liquid engine, and there I said the chamber pressures are of the order of 200 bar, right, and I said somewhere in the pipeline it is going to be something of the order of 300 bar or above that. If you look at the coolant pipes, they are going to be very, very small, right, and there is an enormous pressure drop in pushing liquids at a very high rate through these small pipes. So if you are going to use regenerative cooling, the penalty that you are going to pay is in terms of pressure loss. Okay. Pressure drop, in other words, is also going to affect, if you are using a turbo pump to pressurize it, there is some amount of energy that is expended which is not going to impact the ISP, right. So in that sense it comes back to a reduction in ISP. But as we said earlier, in this method you are pumping back the heat that is lost to the walls. So you are going to take it closer towards the adiabatic condition that we had assumed while we were deriving equations. So in that sense there is a gain in ISP because it is going to be adiabatic, and there is some amount of loss because there is something that you need to pay for the pressure rise or the pressure drop across the coolant channels. And radiative cooling, as we had discussed earlier, I had clubbed it with heat sink because this also needs to have a certain amount of thickness, right. So again the penalty here is weight, okay. So we have discussed all the cooling techniques that are used on board a rocket motor, and if you look at it, if you have a liquid engine, regenerative cooling is probably the best method of cooling. But if you look at some of these aspects, you need to have a certain amount of backup or redundancy if you are restarting and if you have throttling and other things. So invariably people also tend to use film cooling to back it up or to add redundancy into the system so as to have a safer margin, okay. Although it is not so efficient, film cooling has been used and will continue to be used because it gives you that little bit extra that you can do even after designing everything, right. Even after you design the motor, everything is done, you still have that margin to play around with because you have this film cooling. So if we look at a picture wherein what are the regimes that each one of them is going to be used in, it is going to be something like this. So if you have burn time on the y axis in seconds, and this is on a low log scale, and thrust also on a log scale, so you can divide this into various regions. If you see that you have a smaller burn time and whatever thrust level that you want to have, it is possible to use heat sink. But as the burn time increases, you also need to back it up with ablative cooling, and for a very low thrust and large burn time, it's better to use radiative cooling, and the region for high thrust and high burn time, it is regenerative cooling. and I have not indicated where film cooling is. As I said, if you are using a liquid engine, it can be used everywhere in this domain. It is to add some kind of redundancy, and therefore can be used all across the domain. Okay. So this completes our discussions on the various cooling techniques to cool the rocket motor nozzles. Now let's look at we are discussing about a liquid rocket motor, and we know that it has to have a feed system. Either it is going to be pressure fed or turbo pump fed. Let's try and look at the design of the feed system. So firstly, let's look at pressure fed systems. If you look at the figure of a pressure fed system here, if you look at this figure, what we are essentially going to do is, if we are given, see, when we are asked to design the pressure fed system, what we are going to do is try and design this size of the gas bottle. What is the size of the gas bottle that we need to carry, and at what pressure, so as to have a chamber pressure of certain value, okay, fine, and for a burn time. So essentially you will be given, for doing this, going about doing this, you will be given firstly the thrust time curve, which means that you know what is the thrust F and you are also going to know what is the burn time. TB, right? After knowing this, let's say you are going to use some kind of propellants, right? If it is a bipropellant system or a monopropellant system, you know what are the propellants that you are going to use, and if you know the chamber pressure, PC, and you also know the area ratio of the nozzle, and propellant combination. So you are knowing from this propellant combination, what you can get out of this is the chamber temperature, and you know the area ratio and the chamber pressure and also the ambient pressure or its variation, right? So you can calculate what, knowing all this, you can calculate the specific impulse of the motor, right? So at the end of this you will get to know what is the specific impulse. if you know the specific impulse and if you know the thrust, what can you calculate? Mass flow rate through the motor, because we know that m dot is nothing but F by ISP. So you can calculate what is the m dot, and after knowing what is the m dot, you can get depending on the ratio of fuel air ratio, oxidizer to fuel ratio, right. You know the overall mass flow rate and you know the ratio of fuel to oxidizer, that is, let me call this as S. Okay. Then you can calculate the individual mass flow rates of oxidizer and fuel, right. So if you can calculate the individual flow rates of oxidizer and fuel, and then you also will know the density of these materials, right. So you can get volume flow rate of oxidizer and fuel, and now you know the burn time. So you can calculate the overall volume of the fuel and oxidizer that you will need for the particular machine, right. But is that going to be enough? If you just do this calculation and carry that much of liquid on board, right, you will know the burn time. So you carry based on this whatever is the volume of the liquid. Is that going to be sufficient for your fulfilling the mission? Huh? No? Why? What kind of losses? Yes, if you look at any kind of feed system, there is some amount of fluid that you might not be able to expel out of the tank itself, and obviously there is going to be some kind of fluid depending on what kind of cooling you have. If you have regenerative cooling, then a larger fraction of the coolant is going to be trapped in the pipes, okay. So that is not going to be useful. So you need to carry a slightly higher volume than what you get from this, typically of the order of 2 to 3% extra, okay. So if you then estimate what is the volume, it is going to be 2 to 3% higher than this volume. So now you know what is the volume of the fluids you need to carry. In addition to what we discussed, if you look at if you are using cryogenic propellants like liquid oxygen and liquid hydrogen, after you store it in the tank, right, and keep the vehicle ready for takeoff, as it continues with its operations, because of the temperature difference, there is going to be some amount of boiling of this propellants, right. So these are not going to be useful because it is already going to become a gas, and therefore it is not going to be useful. So you have to account for that also while calculating the overall volume that is required, okay, fine. So once you calculate all this, taking into account all this, you are going to calculate some volume. Now if you look at this design here, you are not going to fill the tanks completely because then there would be no space for the pressure end to act. So you are going to have a small amount of volume that is left unfilled, through which the pressure end can act, right. So if we were to design what is the pressure end, how much is the amount of pressure end we need to calculate carry on board, we need to know the volume flow rate, and from the volume flow rate calculate the overall volume, then account for losses like boiling and some coolant trapped in the pipes, and also you are going to have a small extra volume known as ullage volume. So if you account for all this, and then you know what is the tank volume, right. Now this tank has to be filled at some pressure by the pressure end system at the end of burning. If you look at it, so the pressure inside the tank should be the same as what we started out in the beginning, if we are not doing any thrust variation. So you need to take into account what is the volume of the tank and what pressure it is going to be stored at the end, and then calculate what is the volume you need to have, and that will help you size the pressure end tank. So if you look at doing that, so the weight of the pressure end would be mg is equal to, this is given by ideal gas law, multiplied by a compressibility factor okay. This Tg is the temperature of the pressure end gas, then Pt is the Vt is the volume of the tank, and Z is the so using this you can calculate what is the mass of the pressure end. Okay, we will continue with this in the next class. Thank you.